Welcome to geometry class. We're starting a new unit today, and this unit is called reasoning. So we use reasoning as a tool a lot in geometry to figure things out and to prove that things are what we believe they are. The first type of reasoning that we're going to focus on is called inductive reasoning. And inductive reasoning, as it says at the top, is a reasoning that uses information from different examples to form a conclusion or a statement called a conjecture. So a conjecture would be like an educated guess, kind of like a hypothesis in science class, or you could think of it as like a prediction. So we are trying to figure out patterns when we're doing inductive reasoning. We're looking for patterns, and we're trying to predict what will come next, okay? There's two example problems fully worked out at the top of the page. I'll leave those there for you in case you need extra examples to take a look at. We're going to do some of these problems down below together. So the first one is an exercise that says write a conjecture that describes the pattern in each sequence. Then use your conjecture to find the next item in the sequence. So for number one, it goes -5, 10, -20, 40. So your job here is to figure out what the pattern is and then to find the next item that would go in the sequence. So what would come after the 40? So some things you might want to notice are that the signs are alternating negative to positive to negative to positive. So I'm going to predict that the next one should be negative. And then if you look at the number, 5 goes to 10, 10 goes to 20, 20 goes to 40. So the absolute value of the term is doubling each time. It's like we're multiplying times -2. So -5 times -2 gives you gives you positive 10, excuse me. 10 times -2 gives you -20. -20 times -2 gives you 40. And then what is 40 times -2? -80. So the pattern is that we're multiplying by -2, and then the next number in the sequence is -80. These types of problems are found on a lot of college entrance exams, such as the TSI, the SAT, the ACT, assessments like that. So these are really good to practice on. Some are easier than others, and that's okay. So then we're going to go 1, 10, 100, 1,000. Can you predict what the next number in the pattern will be? Give you a second to think about it. What is the pattern going on here? Have you noticed we're multiplying times 10, times 10, times 10? So if we take 1,000 times 10, we'll have 10,000. Okay, number 3. The numbers in the pattern are 1, 6/5, 7/5, 8/5. So it kind of looks like these last 3 make a pattern where the denominator is always 5 and the numerator is increasing by 1 on each fraction. But what about this number 1 in the front? Does it fit that pattern? Actually, it does, because if you were to go backwards on this pattern and decrease the numerator by 1, you would have 5/5 for the first one, and 5 divided by 5 is 1. So that's a simplified version of that fraction. So on each one, we are adding 1/5, and so the next number in the pattern would equal 9/5. All right. Now we're going to look into some geometric conjectures. Write a conjecture about each value or each geometric relationship. As a hint, I'm going to suggest that you think for geometric relationships about vocabulary words that we have already learned about this year. So in Unit 1, we learned quite a few new vocabulary words, and those should come into play when we're describing geometric relationships. So for problem 4, we have 3 points given, A, B, and C. So I'm just going to sketch a little graph and plot these points. -1, 0, 1, 2, 3, 4, and then -1, 0, 1, 2, 3, 4. Okay, so I've got the point -1, -1, 2, 2, and 4, 4. What do you notice about the 3 points that I just plotted? Can you think of a geometric relationship that would involve one of the vocabulary words that we learned in Unit 1 that would describe those 3 points? Can you tell that those 3 points would fall along a straight line? If you remember some of your algebra, you might recognize that this is the line y equals x, where both the x and the y coordinates are the same in each point. So the geometric relationship between these points are that the points are, what's that word for points that fall on the same line? Geometry vocabulary word from Unit 1. The points are collinear, on the same line, together on the same line. Okay, number 5 has angle 1 and angle 2 form a right angle. So if you have 2 angles that form a right angle, they could be called what kind of relationship in geometry? 2 angles that form a right angle. We had angle pair words on our last lesson of the last unit. 2 angles that form a right angle are called complementary angles. They are complementary angles. So they could be connected at a 90-degree angle, like say this is angle 1 and this is angle 2. Or it might just be that, say, angle 1 is 45 degrees and there's another angle over here, angle 2, that's also 45 degrees. Those would also still be complementary angles even if they were not connected, adjacent to one another. Okay, number 6. Angle ABC and angle DBE are vertical angles. So I'm going to draw the vertical angles. If you'll remember, vertical angles are 2 angles that are formed by intersecting lines. These vocabulary words that we learned in the first unit are still going to be used throughout the course. A, B, C, and then D, B, E. So there's my vertical angles, angle A, B, C, and angle D, B, E. So we need to describe a geometric relationship between these angles. There's actually more than one correct answer here. You might notice that these angles are congruent. So you could say a conjecture would be that the measure of angle ABC is congruent. Or we could just say the angle ABC is congruent to angle DBE. Or if you put the measure, then you would say equals. The measure of angle ABC equals the measure of angle DBE, because that's talking about the numerical measurements. Congruent means same shape and same size, so both the measurement and the shape are the same. Same shape, same size. Some other things that you might say is that these are non-adjacent angles because they do not share a side. Or you could say the 2 angles share only one point, that being the vertex B. So there's a few different observations, predictions, conjectures that you could write about the geometric relationships that must be going on given that these 2 angles are vertical angles. Okay, number 7. Angle E and angle F are right angles. Okay? So you might want to pause the video and see if you can come up with a conjecture on your own, and then check and see. And you might come up with one even that I don't have written down. But let's say that you've had time to do that. If I know two angles are right angles, I could say angle E is congruent to angle F. They're congruent if they're both right angles. I could write angle E and angle F are supplementary, because if you'll remember, the word supplementary angles means angles that add to make 180 degrees. So if they're both right angles, they would add up to 180. Or you could say the measure of angle E is equal to the measure of angle F. They're not necessarily a linear pair here, because they do not say that they need to be adjacent, so that would be kind of overstepping the required outputs based on the given information. But you may have come up with another answer there besides these two. Okay, moving on to the back. We here are going to determine whether each conjecture is true or false and give a counter example for any false conjecture. So we have the word counter example defined up here, and this is a very important word. We use this a lot in geometry. A conjecture is false if there is even one situation in which the conjecture is not true. The false example is called a counter example. So if you say, well, it's true most of the time, but there is one case where it wouldn't be true. In geometry, we just call that a flat out false statement. If you can come up with even a single example, which we call a counter example, to prove a statement is false, then we say that that statement is false, okay? So if we say true in geometry, we're saying that it is always true no matter what. Now, I want to show you this example. I think this one might come up again. If segment AB is congruent to segment BC, then B is the midpoint of AC. Well, if I draw a line segment like this, and I say here's A and here's C, and I know that AB is congruent to BC, then yeah, B would have to be the midpoint of AC. That's true, the way I drew it right here. But what if I drew it the way you see it shown here below? This is the counter example to show that this statement is false. Is it possible to draw a diagram where AB is congruent to BC such that B is not the midpoint? See, B is not the midpoint of AC in this picture. If I connect A to C, the midpoint would be midway in between those two segments over here. This could be like point D or something. It is not, B is not the midpoint. It doesn't even fall along the segment AC. So this diagram over here shows a counter example because B is not even lying on the line segment AC. So this conjecture, if AB is congruent to BC, then B is the midpoint of AC, is false. It's a false statement, and here is the counter example. So there's a way that you can draw it where it's true, but if there's even one way that you can draw it where this statement is no longer true, then we say this has to be a false statement. So let's take a look at these down here. Number 1, if points A, B, and C are collinear, collinear means along the same line, then then the distance from A to B plus the distance from B to C must equal the distance from A to C. What do you think? You may want to pause the video and ponder this for a moment. All right, so now I'm going to assume that you've paused and you've given it some thought, okay? So let's say I draw a line and I put point A, point B, and point C along this line. Let's say from A to B is 2 and from B to C is 3 units long. Well, AB, distance of 2, Here I'm going to write this AB plus BC is supposed to equal AC. So from A to B is 2, from B to C is 3, and that adds up to 5, and 5 is the length from A to C, so that looks true based on this picture. Is there any way I could draw this picture so that that would not be a true statement? Well, what if I drew a line segment and I said this is point A, and this is point C, and this is point B, and this is 2, and this is 3. Now, is AB plus BC equal to AC? Well, AB is 5, and BC is 3, and AC is 2. 5 plus 3 equals 2. 8 equals 2? No, I don't think so. So this is a false statement, and this is my counterexample right here, because nobody said that point B had to be between A and C. If they had included that, then it would have been a true statement. But since they did not include that, it's a false statement. Number 2, if angle R and angle S are supplementary, remember supplementary means add up to 180, and angle R and angle T are supplementary, then angle T and angle S are congruent. Okay, I suggest that you pause the video and think about this and decide for yourself if this is true or false before I go over it with you. Okay, I'm going to assume that you have done that. So if I have the measure of angle R plus the measure of angle S equals 180 degrees, because they are supplementary. And then I also have the measure of angle R plus the measure of angle T is equal to 180 degrees, because those are supplementary. From algebra, you learned that if you have two things that are equal, you can do a substitution. So I can switch a 180 out with this statement because 180 equals this. So if that also equals 180, those could be replaced. That's called doing a substitution from algebra. So let's say I have the measure of angle R plus the measure of angle S equals the measure of angle R plus the measure of angle T. Okay? Whoops. I'm sorry, I did not realize I was getting off the screen there. So I've replaced 180 with these because these also equal 180. So this part has to equal this part because they both equaled 180. Now, in algebra, you said you can do anything to both sides of an equation. As long as you do the same thing on both sides, you maintain equality. So I'm going to subtract the measure of angle R on both sides. So now I have measure of angle S is equal to the measure of angle T. Now it says angle T and angle S are congruent. Yes, if their measures are equal, the angles are congruent. So this is a true statement. So the first one was false, the second one is true. All right, number 3. If angle ABC and angle DEF are supplementary, then angle ABC and angle DEF form a linear pair. Well, I think I kind of talked to you all about this one already. Just because two angles are supplementary does not mean that they have to form a linear pair, because a linear pair means they share a side. If I draw angle ABC and say, hey, this is a 40-degree angle, and over here I draw angle DEF and say angle DEF is 140 degrees. These two angles add up to 180, so they are supplementary, but they do not share a side. They're not touching at all. They're not adjacent to each other, so they do not form a linear pair. So they do not share a side. So the statement is false, and this picture is my counterexample. Okay, Number 4. If segment DE, and if you'll remember, this upside down capital T means perpendicular to, is perpendicular to. Two lines that are perpendicular meet at 90-degree angles, at right angles. So if segment DE is perpendicular to segment EF, then angle DEF is a right angle. So I'm going to write this down. Is perpendicular to. So here's DE, and then EF is perpendicular to it. So angle DEF forms a right angle. That's true. By the definition of perpendicular lines or line segments, these two have to meet at a 90-degree angle, which is a right angle. So that is true. Okay, we're going to go on, and if you're following along in our textbook, we're kind of skipping around here. We're now going to, excuse me, section 2-5, which is called Postulates and Paragraph Proofs, but I'm not going to have y'all do paragraph proofs. We're usually going to do 2-column proofs in here, maybe a flowchart proof or something, just because they are simpler and easier for students to understand in general. So if you see the directions paragraph proofs, you can just assume you're doing it the way I taught you, which is a 2-column proof. But what is a proof? Mrs. Heiss, you haven't even taught us that yet. Well, here we go. In geometry, a postulate, fancy word here, is a statement that is accepted as true. Postulates describe fundamental, which means basic, relationships in geometry. So we have 7 postulates listed here. These are basic statements that are accepted as true in geometry. So we're not going to have to prove them. They're kind of like almost similar to a definition. They are accepted as true statements. So the first one here, postulate 2.1, says, through any 2 points, there is exactly one line. All right, so I want you to imagine 2 points drawn. Could you draw different lines that pass through those 2 points? I don't think so. That's a pretty basic concept. If you have 2 points, you draw a line, that makes one line. Okay, that's our first postulate. The next postulate, 2.2, says through any 3 non-collinear, which means not on the same line, points, there is exactly one plane. So basically, if I put down 3 points in any kind of triangular fashion, that is just going to create one flat plane that the points are falling upon. Okay. Postulate 2.3. Oh, I'll go ahead and draw a plane around those. A line contains at least 2 points. Well, that's pretty basic because when we talked about a line, we talked about how there's an infinite number of points on a line because it just extends forever. It's an infinite array of points extending in opposite directions. So it does have to contain at least 2. Now what that means is a line cannot contain just 1 point. If you just have 1 point, you can't say, oh, that makes a line. You have to have at least 2 points to create a line. Okay, now postulate 2.4 says a plane contains at least 3 non-collinear points. Well, this sounds a whole lot like postulate 2.2. Through any 3 non-collinear points, there is exactly one plane. This one says a plane contains at least 3 non-collinear points. So what's the difference between those two? They sound almost exactly the same. Well, what's different is what they start with. This one starts with a plane. If you have a plane, then you have at least 3 non-collinear points. This one says if you have 3 non-collinear points, then you have a plane. So it's all based upon what you're starting with. Now the next one, postulate 2.5, says if 2 points lie in a plane, then the entire line containing those points also lies in the plane. So I have 2 points, there's a line going through it. If the 2 points are in a plane, then the whole line is also in the plane. Postulate 2.6 says, if two lines intersect, then their intersection is exactly 1 point. So I have a pair of lines that intersect. The way they intersect is just in one single point. And last, if two planes intersect, then their intersection is a line. This is a little bit harder to show in two-dimensional space because we're talking about a 3D concept here. So let's say I have this purple paper. It's like a plane, and my white paper that I'm writing on is another plane. So if I make them cross, then the way they cross would be in a straight line that I'm making by tracing the intersection. So two planes intersect in a line, okay? And I can't draw you, well, I mean, I can draw you a picture. I'm not a very good artist, but let's see. So this line would be, for example, where the purple paper crossed the white paper. Let me see if I can highlight. So the purple paper was coming up from above, and the white paper was down below. I'll make it yellow. So that when they meet, it's not a flat surface, it's crossing at one line. Okay? Hopefully that helps. 3D models can help with that. If you get a couple of sheets of paper and make them meet, you'll see how they meet at a line. Okay, here are 3 examples that are fully worked out. I'm not going to go through those with you. You can read over those if you need more examples to look at. We're going to begin down here where it says, determine whether each statement is always, sometimes, or never true. So in the other lesson, we talked about how in geometry, a statement, if it is true, has to always be true. So a true statement is like always true. Now, we said anything that wasn't always true was false. But here we're not doing true and false. We're saying, okay, maybe if it's sometimes true and sometimes false, we're going to go ahead and write sometimes. And if it's absolutely never true, then that's a completely false statement, okay? Both of these are technically false, but we're going to be a little bit more specific in how they're false. Is it sometimes true and sometimes false, or is it absolutely never a true statement? So that's what we have to figure out down here. So, number 1 says, a line contains exactly 1 point. Well, let's look back at these postulates. Postulate 2.3 says a line contains at least 2 points. So could this be always true, sometimes true, or never true? Thinking back to what we said postulate 2.3 was. I'm going to say that that is never true. And I'm going to go ahead and write, it doesn't tell us to write which postulate we use to figure that out, but I'm going to go ahead and include that here. So it's postulate 2.3. A line contains at least 2 points, which makes us know that a line containing exactly 1 point could never be true. All right, number 2, non-collinear points. Remember, non-collinear means not on the same line. Non-collinear points, R, S, and T, are contained in exactly one plane. What do you think? Look back at postulate 2.2. Through any 3 non-collinear points, that's what we're starting with, 3 non-collinear points, there is exactly one plane. They are contained in exactly one plane. Yes, this is always true based on postulate 2.2. Okay, number 3. Actually, why don't you pause your video and try number 3 on your own? All right, I'm going to assume you did. Any 2 lines, L and M, intersect. Well, we have a postulate about intersecting lines right here. That was postulate 2.6. And it said, if two lines intersect, then the intersection is exactly 1 point. But that's if they intersect. So do they have to intersect? I don't think they have to. It says if they do. If they do, maybe they do, but maybe they don't. So, oh, excuse me. Any two lines, L and M, intersect would be sometimes true because of postulate 2.6. It says if two lines intersect, so they don't have to. They could. Maybe they're not intersecting lines. Maybe they're parallel lines. Or maybe they're skew lines, you know, when they're two lines that don't intersect that are not even in the same plane as each other. So sometimes. All right, this next one has an error in it. It says if points G and H are contained in plane, there's a little rectangle with a question mark there. That was supposed to be a capital cursive M, but for some reason the computer doesn't like the font that we used. So if points G and H are contained in plane M, then segment GH is perpendicular to plane M. Okay, so what are we starting with? 2 points in a plane. So here's my plane M, and I have a point G, and I have a point H contained in the plane. So GH is perpendicular to plane M. Perpendicular would mean that it forms a right angle to the plane. That would mean more like it's coming up off of my paper directly straight up in the air like a pole on the ground to form a 90-degree angle. So this is never true because it's not at a 90-degree angle if it is within the plane. Which one tells us that? It's postulate 2.5. If 2 points lie in a plane, then the entire line containing those points lies in the plane. So we are going to say 2.5 is the postulate we're using there. All right, number 5, planes. This was supposed to be a capital cursive R. I don't know why it likes my cursive S and not my R or my M, but I apologize. Planes R and S intersect in point T. What do you think? Two planes intersect in point T. Postulate number 2.7 says if two planes intersect, then their intersection is a line. And a line contains at least 2 points. So can they just intersect at point T? No, that is never true. And it is by postulate 2.7. It has to intersect in a line, not a point. All right, number 6. If points A, B, and C are non-collinear, so not in the same line, then the segments AB, BC, and CA are contained in exactly one plane. What do you think? Always, sometimes, or never true? You draw a little picture. They're non-collinear. A, B, C. So segment AB, BC, and CA are in the plane. Exactly one plane. I'm going to say always, because of postulate 2.2, through any 3 non-collinear points, there is exactly one plane. We've got 3 non-collinear points, so they have to all be in exactly one plane. You might have thought it was 2.5. If 2 points lie in a plane, the entire line containing those points also lies in the plane. It's actually kind of a combination of those 2 postulates, so either one of those referenced there would be appropriate. Okay, moving down to the bottom here, it says in the figure, this picture right here, Segment AC and segment DE are in plane Q. Segment AC is parallel to segment DE. So I'm going to put these little arrows on this picture. That's going to indicate that these lines are parallel to each other. State the postulate that can be used to show each statement is true. So this time they're not asking us, is it true? They're saying, yes, this is true, but which postulate would be the one that makes it true? So for number 7, it says exactly one plane contains points F, B, and E. So that is a true statement. Now I know that they didn't draw a plane through F, B, and E, but through any three non-collinear points, there is a plane. And that is by postulate 2.2. So whether it's drawn in the picture or not, any three non-collinear points form a plane. Then number 8 says line BE lies in plane Q. Well, again, they didn't draw the line through BE, but any 2 points we could draw a line through if we wanted to. So from B to E we could make a line, and that line would fall in plane Q because of postulate 2.5. If 2 points lie in a plane, then the entire line containing those points lies in the plane. Okay. We're going to go on to the back, and on the back it talks about paragraph proofs. So I told y'all we're not going to do them in paragraph format. I have found most geometry students don't particularly enjoy writing full, complete sentences in paragraph form over the years. So we're just going to do 2 columns, but the concept is the same. A logical argument that uses deductive reasoning. So on our other sheet, we were talking about inductive reasoning. This is deductive reasoning, which is a different type of reasoning. Instead of looking for patterns, we're looking to make a proof of something being true based on known facts. So we're not relying on our guesses, our hunches, our explorations. We are looking at what are the facts, what do we know. We can only base everything off of a known fact. This is the type of reasoning people use in like courtroom cases. You have this list of facts, so what conclusion could be made based upon these given facts? Okay, so a logical argument that uses deductive reasoning to reach a valid conclusion is called a proof. So that's the definition of a proof, okay? In one type of proof, a paragraph proof, you write a paragraph to explain why a statement is true. And like I said, we're just going to do 2 column proofs. A statement that can be proved true is called a theorem. So there's the definition of a theorem, something that you can prove true. You can use undefined terms, definitions, postulates, and already proved theorems to prove other statements are true, okay? So we've got a lot of vocabulary going on here. For our first proof, we are going to do problem 2, just problem 2, and that will be enough for today. So it says, it is given that segment BC is congruent to segment EF. So look at these 2 segments, BC and EF. Those are congruent segments, okay? M is the midpoint of segment BC, and N is the midpoint of segment EF. Write a paragraph proof to show that the distance from point B to M is equal to the distance from point E to point N. Okay, so that can be done in more than one correct way. Proof writing is something that you get better at the more that you do it, but I do not expect you to be an expert on day 1. I'm going to give you, I think, maybe one little thing to practice with proofs in your assignment today, but it won't be very much. And we will be working on this more as time goes on. So for problem 2, we're going to set it up. Let me see if I can get my paper, because I'm going to need some space. We're going to set it up with a T-chart. Okay, and I'm just making this first one big, probably bigger than I need to. And so this is problem 2, and I'm going to put statements on the left. This is always what goes at the top title of your T-chart, and reasons on the right. And the first thing that goes under statements is whatever they give you in the problem. So it's given that segment BC is, let's see if I can pull this down, congruent to segment EF. And this is, the reason I know that is it was given in the problem. The first reason is always given. The first statement is always whatever they give you in the problem, okay? What else are they giving to us? M is the midpoint of segment BC. So number 2, M is the midpoint of segment BC. And that is also a given statement. And then we have one more given statement. See, it's given that this, and this. So there's 3 things that are given in the problem. The third thing is that N is the midpoint of segment EF. So I have 3 given statements in the problem that I can start with, okay? It's usually a good idea too to go ahead and draw the picture that you're working with nearby your proof so that you can refer to it as you are working. So I'm going to go ahead and sketch the picture. I have BMC and I have ENF. Okay, so I have 3 things that are given, and I'm trying to prove or show that BM is equal to EN. Whatever they give you for your show statement is what you're going to want to end with in your proof as your last statement. So if M is the midpoint of BC, then what do I know about BM's length there? Wouldn't BM have to equal half the length of BC? And what do I know about EN? Wouldn't EN have to be half the length of EF? EN is half the length of EF. How did I know that? Because of the definition of midpoint. Remember, a midpoint separates a segment into 2 equal parts, each one being half the length of the whole. So, how does that help me? Well, if we knew that segment BC was congruent to segment EF, then that means BC, the distance from point B to C, would have to equal the distance from E to F. So this statement 5 comes from this statement 1, and that is because of the definition of congruent. Okay, if 2 segments are congruent, then the distances from their endpoints are equal to one another. Now, if you remember in algebra, we have this rule. These are numbers once we've written the equals between them. We have the rule in algebra that you can just do the same thing to both sides of the equation. Notice here I have a BC with a half in front of it. Here I have an EF with a half in front of it. What if I multiply both sides of this equation times 1/2? 1/2 times BC would have to equal 1/2 times EF. And I did that by the multiplication property of algebra. In algebra, we know that we can multiply an equation by the same number on both sides of the equation and maintain equality. Okay, so now I have 1/2 BC is equal to 1/2 EF. Well, up here I said 1/2 BC was equal to BM. Could I take out this 1/2 BC and replace it with a BM? Sure I could, by the substitution property of algebra. Could I also take out this 1/2 EF and replace it with an EN? Sure I could. Substitution property of algebra. Okay, and notice, this was what I was trying to show. The distance from point B to M is equal to the distance from point E to N, and that's what I have just shown. So I have finished this proof. Okay, I know that the first time that you see a proof in geometry that it can be a little bit daunting. So don't worry if you're feeling like, what's going on here? It's okay. We're gonna spend more and more time on this. This was just our very first one, okay? And you will get it in time. It's gonna take some practice and some, not just watching me do it, but some little working things out and looking for patterns and seeing how things go over time. So I know you'll be fine and you'll be able to do this. But I hope that you've enjoyed learning about inductive reasoning and deductive reasoning, and some new words today like counterexamples and theorems and proofs and postulates and lots of big important words in today's lesson. But have fun with your assignment, and I look forward to seeing you for our next lesson. Have a great day. Bye.